This talk is to discuss the history of plate motions along the Pacific Australia plate boundary south of New Zealand. I'm going to review results from a number of years from different cruises that were designed to study the tectonics of this area. Let's see how we do here with the advancing slides. This is my brief self-introduction, and I think you covered all of it. So the only thing I will add is that I actually worked for the government, the United States Geological Survey, from 1982 to 1984, in between doing my master's degree and my PhD. And I did hydraulic fracturing stress measurements for earthquake hazards. But the rest of this is similar. And I've been on 15 research cruises, 10 of which were on the Nathaniel B. Palmer, which is the US Antarctic icebreaker. 2 of them were drilling cruises on the JOIDES Resolution, including the South China Sea drilling cruise that you mentioned. And then we've also done seismic reflection surveys on 3 other ships, including the Ewing, the Langseth, and the Ulloa. So what I'd like to show you today are what we know about the modern plate configuration and kinematics south of New Zealand, the past history, assuming that the plates were rigid, and it turns out they weren't really rigid. So that's part of the challenge of understanding what happened in this area. If we change the history to allow for deformation of continental regions, which we now recognize was important, that helps us understand how subduction initiated in this region and also gives us implications for future evolution of this plate boundary zone. You've probably seen this information about how the polarity of subduction changes from north of New Zealand to south of New Zealand. This shows GPS velocity vectors averaged over the past 5 to 10 years relative to the Australian plate. And so you can see that Australia is the upper plate to the northeast where the Hikurangi Trench starts. And then to the southwest, the Australia plate is actually getting subducted again under Pacific. So if we look at Demetz et al.'s Morville model of the 25 plates, the Indian Ocean shows some rigid plates, which include India, Capricorn, Australia, and Macquarie, and then some zones of diffuse deformation, which are between India, Capricorn, and Australia. And then this boundary between Australia and Macquarie shown here. And I don't know if I can use a mouse, but maybe you can see this. Can you see my finger? This is dashed because we don't actually know exactly what this boundary looks like. So Demetz et al. Came up with this model, and you'd want to know, well, what is it that led them to think that Australia and Macquarie are 2 separate plates? It turns out that Demetz et al. Earlier in 1998 had suggested that this should be called the Macquarie Plate because there was significant seismicity off of the plate boundary in the southeastern corner of the Australia Plate. And so this is what they proposed in 1988. And this led to then this kind of interpretation where the evidence for the existence of the Macquarie Plate includes the fact that there are zones of diffuse deformation within the Australia region, including these 2 green ones and then this yellow one. But between 88 degrees east longitude and 139 degrees east longitude, it looks as if Australia and Antarctica had a pretty rigid behavior and a good spreading history. But then the data in the region that's yellow here seems to be characterized by diffuse deformation. And so part of what we want to know is, well, exactly what happened there. Is the Macquarie Plate just in this region that's marked in MQ in this picture? And so I went back and summarized for you this, the earthquakes that happened from 1960 to 2022 that are in the catalog from the USGS for magnitude greater than 4.5 earthquakes. And you can see on the left here, all these red dots are the earthquakes that show up in the catalog for that time. So they roughly follow the trace of the Macquarie Ridge Complex. The Macquarie Ridge Complex is on the right-hand side of the slide here. And it consists of several different segments of the boundary between Australia and Pacific. These are labeled P for Puysegur, MD for McNougal, MQ for Macquarie, and then H for York. And what's interesting is that not all the seismicity is just on this boundary of the Macquarie Ridge complex, but there are some earthquakes that are off the Macquarie Ridge complex to the western side. And so this isn't as simple as the idea that you just have a band of deformation between Australia or in the Australia plate between Australia and Macquarie, but it gives you an idea of what to look at when we're thinking about understanding the tectonics here. This interpretation, which is a more detailed look at the geometry of the Macquarie Ridge complex, comes from Meckel et al. 2005 in D cubed on the left, where Meckel has labeled the Puysegur Ridge and the Puysegur Fault in the Puysegur segment in the north. Then the McDougall segment, which is labeled MD in the middle picture, is just a very straight fault system that doesn't look as if it's gotten any significant convergence. The MQ segment is the region where Macquarie Island is above sea level, and Macquarie Island has a trench as deep as 6 kilometers depth below sea level on the eastern side of it. So if we're looking at this geometry and we're trying to decide, well, where's actually the Macquarie Plate? It's not clear from this information whether there's an obvious boundary between the Australia plate and these other parts of the plate system. So the way that people normally might draw this, if you can see my mouse, where this big boundary is here between Australia and Puysegur, some people just drew the boundary there and they said, well, this all here below this is that okay? Can you guys see that?
I'll see it closer.
Okay. There might be a way to change it. Oh yeah, there you go. Perfect, thank you. Okay, so now it's nice and red. Can you see it? This boundary here between Australia and Pacific, Puysegur, it shows up in the bathymetry here. And this is an old rifted margin from when Australia plate broke off from Antarctica and Pacific long earlier. We'll talk about that in the history of the deformation here. So anyway, to just finish off the story of what's happening here at the southern end of the Hikurangi Trench, there's a recent paper that came out in Geology in 2023 showing that how the Hikurangi Trench connects to the strike slip system here between Antarctica and Pacific in this region, and the spreading system between Macquarie and Antarctica. So you could take a look at this if you would like more detail about what's going on down there. But this doesn't help you determine where the Macquarie Plate is and sort of what its northern boundary is. And so for this, we can look at some other kinds of information in addition to the seismicity that we looked at. And these are two other interpretations. This is showing you the gravity data, and you can see that rifted margin that shows up very well here. And then the rifted margin here on the south side of Australia is where Meckel et al. Drew the boundary between Australia and Macquarie. So in that situation, the boundary would run right up into the South Island of New Zealand. And the red lines here were drawn by Meckel et al. To show where they thought that plate boundary slip was taking place in this region. So they didn't show a diffuse deformation zone in here. However, from the seismicity and from the Metz et al. 1988 work, we would infer that it might be something like this was just from the Choi et al. 2017 interpretation, where they looked at a lot of seismicity coming into the South Island of New Zealand and inferred that maybe this whole zone could be considered a diffuse deformation zone between the Australia plate and the Macquarie plate. So this is still somewhat an unresolved issue, but in the meantime, we wanted to look more at the plate circuit for what had happened in this region around the Alpine fault and to the Puysegur area at the northern part of the plate boundary south of the South Island of New Zealand. And this is what we typically do when we're trying to do a plate circuit. is we can sum the reconstructions of how the plates close up for times in the past by using magnetic anomalies and fracture zones along known spreading boundaries. And so we have spreading boundary number 1 here, which is from Pacific to Antarctica. And we have spreading boundary number 2, which is from Antarctica to Australia. And when we combine those, we can get the history of what happened in New Zealand itself. And so just to review really quickly about this, we use the magnetic anomalies in mid-ocean ridges. We identify them based on magnetic surveys on ship tracks. So you'd be picking these anomalies, assigning them points, and then you would come up with a set of points for your study area. In this case, these are the ones that we thought were rigid motion between Australia and Antarctica. And those are all west of this George V fracture zone, because we were worried that all the points further to the east might have been contaminated by diffuse deformation due to Macquarie Antarctica spreading. So this is the set of points that we had for the Australia Antarctica side. And then we did a bunch of cruises going back to the 1990s from actually even earlier than that. There's some here from 1997, where we specifically ran marine magnetic surveys to try to determine what the spreading history was and collect points that were missing down along the Antarctic margin to try to get the Pacific Antarctic story put together. So then we can do Pacific to Antarctica, then Antarctica to Australia. And just to give you an example from another part of the ocean that's a little bit better known, here are the points for the South Atlantic from Seaton et al. 2014. And you can see that we go from these points, which are positions that were determined from ship tracks, to a model that has all these lines filled in. So now there's like isochrons everywhere based on it, trying to fit these points to what the age of the seafloor would be. And so then what you can do if you want is you could remove the seafloor that's younger than what you're looking at. If we do this for the South Atlantic, we'd end up with 3 separate plates with all these 0 to 5 million year old seafloor removed, and we'd end up with a set of reconstructions that we could close this back up and say, well, this is what it looked like 5 million years ago at this triple point. And so that's the kind of thing we're trying to do for south of New Zealand, but with the problem that we don't really have the isochrons very well for the directly in most of the cases for Australia to Pacific. So we have to go around this plate circuit to get the answer. And the other information that we use for this is multi-beam bathymetry. So in addition to using the magnetic anomaly points, we would do surveys like this one where we get multi-beam and magnetics along tracks where we could then pick out what happened in terms of this plate tectonic history. So when we did all that, we were able to make models of what the age of the seafloor was here. And so these are seafloor spreading provinces between Australia, New Zealand, and Antarctica. And in this picture, this is a modern situation. Here's the South Island of New Zealand in black. The other Australian continent is in black if it's above sea level. So this is Tasmania. The Antarctica that's above sea level is also in black. And then in orange is the continental area that's submerged. So it's still considered to be continent, but it is below sea level. And so this is the Campbell Plateau and the Chatham Rise. And the colors tell you which seafloor spreading ridge produced the seafloor that you see now. And so this red business that's really tiny here is little tiny red wedges from East Antarctica to West Antarctica. There was some seafloor spreading. The pink part here is Pacific to Australia spreading back at the time when this was active as a rift. There's this purple area that's Macquarie Antarctica spreading. This light green is Australia to East Antarctica. The blue is from Pacific to Antarctica. Sorry. Yeah, is that even on here? Yeah, Pacific to West Antarctica. And then the green, light green is Australia to East Antarctica. So this is showing you what we think happened in terms of the origin of the seafloor. And so It's not, it was formed by a single spreading ridge, but then accreted to both of the plates. So the color isn't telling you what plate it is, it's telling you which ridge formed it, basically. And then what happened here was that when the Macquarie Plate formed, it formed by deforming part of the Australia plate. And so it broke off and started, it somehow broke off from Australia and began spreading separately from East Antarctica and producing this zone of purple here. And so we actually started this project because we were trying to study rifting between East and West Antarctica to understand what happened down in this region here. And you'll notice there's a little bit of yellow material here formed by the Tasman Sea when the Zealandia was spreading away from Australia. And then there's another little bit of that same crust that's down here that's now stranded next to Antarctica because the tectonics in the meantime broke it into two different pieces. So if we go back and look at the matching rift margins that are in the former Tasman Sea crust, here's the former Tasman Sea crust in yellow. And you see there's a little tiny piece of it right in here that's south of the Campbell Plateau. And there's another little tiny piece of it here that's off of part of West Antarctica. And so the idea is that we can match this rift margins very well because we have a lot of seismic reflection profiling and multi-beam studies and marine magnetic anomalies. And so we know that this part here, this is like number 1 and number 2, this South Tasman rifted crust here matches back to the number 1 and number 2 right here. Okay. And then number 3, which is a Neladan rift, which is between the green crust and the yellow, actually matches back here to number 3 here, which is down by Antarctica. And so what you'll notice here is that the matching rift, there's a rifted margin here from 1 to 2 that matches to this one, but then there's another rifted margin here west of the Campbell Plateau, and that doesn't have a conjugate. So if you go looking on the other side, on the Australia side, you don't see anything that would indicate what this broke away from, which is weird, right? It's like you should have the other side of the rift system and we don't have anything to match it. And so we were not as worried about this as we should have been. So I'll show you what happened when we kind of focused on it in more detail. So we did this, before we got around to that, we did this plate circuit reconstruction of the Antarctica by, going from Pacific to Antarctica to Australia and looking at what happened to the 3 plates. And so this is an animation that, let's see if it works. Let's see, how do I start it? There's something funny I need to do to get it started. Oh, there we go. Thank you. Okay. So this is using these isochrons of seafloor age, which are all made from the magnetic anomalies that were observed from all the seafloor surveys. And it's showing you how we would close up the spreading that happened in this part of this Southwest Pacific to get back to what the configuration of the continents was before the rifting began. And so we're going to look at this again. Let's try going back here. Oops. Click the, oh, this one. Okay. So I'm going to try to stop it if I can. Let's see. Stop. Nope, I can't. Okay. Well, the idea is that you can watch if you can stop it little by little. Yeah. Okay. This is showing you how many millions of years in the past you have to go as you look at these pictures. And so 16 million years ago, we basically had spreading between Pacific and Australia, Pacific and Antarctica on the right. And we had spreading here between Australia and East Antarctica on the left. And then there was actually a boundary here between the North Island and South Island of New Zealand. This is what's going to turn into the Alpine fault system. And so let's see. The middle of the middle of here. Okay. Let's see. Okay, if I can stop it. Okay, so okay, so what I want to do is take this back to a time when these rifts were first starting. Okay, see right there, there's a red rift here that's going to, it's cut off the Tasman Sea crust, which is this crust here. And this rift here between Australia and West Antarctica, sorry, East Antarctica.
Is this what you're mentioning, or this rift?
Well, actually, this one first. We'll stop there. 47 million years ago. This is after the Tasman Sea stopped spreading. And so a new rift was breaking through here to form. Yeah, that one. Oh, yeah, thank you. Should I just, you can point to it. Great. Okay, yeah. So look at the red spreading system between, this is between Pacific and West Antarctica. And then it's gonna, let me go back a little bit more. Okay, stop. Okay, here now the Tasman Sea is spreading. You can see that 60 million years ago, the Tasman Sea was active. It had a big spreading center in it. And the parts of New Zealand that are continental actually didn't have a boundary. Okay, so they were all together in one piece. And that piece, which is Zealandia, was actually moving as part of the Pacific plate away from Antarctica and away from Australia along that rift system. And this other rift system here between Tasmania and Australia and East Antarctica was really skinny and going really slowly. Okay, so anyway, so we have this video. This video was made assuming that all the plates are rigid. And so there's abandoned rift and fossil plate boundaries here that are showing up in green. I think you can see them in a few places where there used to be, there's like a V-shaped ridge system or fossil boundary system here by West Antarctica where the two plates were moving separately. One of them is getting subducted under the Antarctica and the other one is spreading away. So there's this whole earlier history of what was happening there, but what we're trying to focus on now is what happened right here. And so we'll go back and look at this one more time, maybe. Let's see if we can. All right, no, we can't. Okay, then never mind. We'll just keep going. Okay, so if we use Australia to Antarctica rotations, then we try to look at what the positions of points are on the Antarctica plate. Now I have to go back to that pointer. Thank you.
Sorry.
That's perfect. Yeah, thank you very much. Okay, yes. Okay, so we go back here, and these are the points that we have that we know are on Antarctica. And they formed by spreading between Antarctica and Australia. And so they should have a conjugate seafloor on Australia that's the same length as what was, because it was produced at the mid-ocean ridge, there should be equal amounts on both sides. What you see is that part of these crons here, this is like cron, what is that? Oh, it's like cron 6. Oh, these 6 and 8, yeah. Okay, so these here, this seafloor that was 20 million years old, which is cron 6, and seafloor that was 26 million years old, that was cron 8. These are too short. There's like stuff missing compared to what ought to be there based on how much is on the other side. So what it means is that some of this seafloor here got overridden by this part of the Pacific plate during the development of the subduction system south of New Zealand. And so if we also use just Australia and Antarctica for these fits, it turns out that the fracture zones don't work either, because part of this whole system down here was actually Macquarie Plate. And so if you look at motion near the Macquarie Triple Junction, this Macquarie Triple Junction is this region currently between Pacific, Antarctica, and Australia. You see that the dashed lines, which are the Macquarie Pacific rotations, which would be small circles about this purple area of Macquarie Pacific relative rotation pole. They fit better if that section is actually Macquarie Pacific, and therefore it would be Macquarie, it would have like a different direction compared to if it was Macquarie Antarctica, or sorry, yeah, in Australia Pacific, sorry. And so the Macquarie Pacific motion, if it's actually just confined to this region, it shouldn't make a difference to what we get for the South Island of New Zealand if all of the plate motion up here is actually the Australia plate and not the Macquarie Plate. But if the Macquarie Plate actually extends all the way up here, then we're getting the wrong answer. So this is something we need to figure out like where the Macquarie Plate was, how much of this motion might have been due to sort of capture of the Australia plate by this new plate Macquarie out of the same seafloor that used to be Australia Pacific. So if we compare this all together, what we end up with for the Macquarie Plate might be something like this orange region, where the missing crust that should be matching to the Antarctica side is here where this yellow color is. And it looks like what was happening in this region was that Australia Pacific was becoming more convergent, and maybe that was triggering the deformation that resulted in part of this former Australia Plate crust being then sort of moved onto this newly established plate, which was called Macquarie, which may be part of the reason why we have different types of tectonics here along this boundary. If we go back to looking at the Pacific, what we call the Pacific Australia Trench and Strike Slip system, that's south of New Zealand. So if we go back here and we take a look in more detail at these boundaries, here again, this is the Puysegur segment, and this is that trench and the strike slip fault system. This is the McDougall that's pretty straight. This part is Macquarie. It's called Macquarie because Macquarie Island is on it. There's too many things named Macquarie in this talk, sorry, because there's Macquarie Triple Junction, which is like down here. And then anyway, the Macquarie Island segment is the one that we're now really trying to focus on to see if we can tell where the seismicity is happening, and if that helps us define where the Macquarie Antarctica boundary is. So Meckel et al. Showed that we had like they had these surveys along the Macquarie Ridge Complex and looked at the tectonics from Puysegur to McDougall down to Macquarie and then down to Hikurangi Trench. In addition to that, we have information from these two transects here that are showing earthquakes, and so there's slightly deeper earthquakes underneath the South Island of New Zealand, indicating that subduction has started here. So this is a zone of incipient subduction. And then the Puysegur Trench is thought to be the location of where subduction is starting. Here, it's going to go into this region west of Fiordland, where there's a big strike slip fault system, or thrust and strike slip fault system. So what we were trying to do when we surveyed the Puysegur segment was to go look at exactly what was going on in terms of how subduction had been getting started right in here. And so we did this survey on Marcus G. Langseth cruise MGL 1803 to study the subduction initiation. This project was called SISIE for the South Island Subduction and Initiation Experiment. This was first published in Earth and Planetary Science Letters in 2019. And then we have some more detailed work that has been done that I'll be showing you. But basically, we did 2 configurations of a streamer, some of which was 12 kilometers long. And then when the weather got bad, we used a shorter one, 4.05 kilometers long. We did multi-channel seismic profiling, and we also shot to OBSs. So we had ocean bottom seismometers along the 2 lines. There were 43 sites because we put down half of them on the first line and then picked them all up again and then moved them to the second line, and only lost 1 OBS. So that was good. We also had multi-beam swath bathymetry, a Knudsen 3260 sub-bottom profiler, a Bell gravimeter that's built into the Langseth, and we had a magnetometer that we towed when we could to look at the magnetic field. And so this is the overall tectonic setting of where we did the survey, and you can see more results that I'm going to show you shortly here in this paper by Schuck et al. That was published in 2021 in Tectonics that shows a lot of seismic data for this Puysegur margin, which is in this box right here. And basically our 2 profile lines across this margin are the ones shown in these yellow dots. And these are the 2 lines where we put down the ocean bottom seismometers and also did the seismic profiling to take a look at what the crustal structure was. And we called these Sissy 1, which is the southern line, and then Sissy 2, which is the northern line. And this is showing you some of the earthquakes that have happened in this region. And our goal was to understand what was going on here in this part of this seafloor, which is called the Solander Basin, which we had thought initially, or, people had thought without really thinking about it, that it was probably oceanic crust. But it was the part that was missing the rifted margin that we had further south, that we didn't have anything matching to it. We couldn't quite figure out what to do about it. So you can look in more detail at that Shook et al. Paper, but basically this is showing you some of the ray paths that we got from the shot gathers and receiver gathers from the different OBSs. And what we were trying to do with this was determine whether we had oceanic crust on one of these lines, and if so, where it was. And it turned out that all of these lines looked like, instead of being oceanic, they were actually extended continental material. So this is what we came up with in terms of the seismic velocity models for the two lines. And there's different degrees of resolution here, which you can also see in the paper. But basically, these are the places where they had the OBSs. So each of these numbers, like 105, 106, 107, 108, etc., is an OBS location that was used to help generate the ray paths and the velocity models that led to this interpretation. And so what we ended up with when we were done with all this, and this is what Brandon Shuck did in his PhD thesis, is that we ended up with models where you could see in detail from the multi-channel seismic data where the faults were, what the subduction system looked like, where it was starting here, and then what's on top of it, and what the fault systems look like above it, and how much subsidence there had been with time. It's really a great story for understanding what happened here. But what you see is that none of this region on either of these lines actually looks like it's truly oceanic. The oceanic crust should be thinner than what we see on the upper plate on either of these sides. And so just to explain this middle figure, because I guess it's a little hard to see. The middle figure shows you the multi-beam swath bathymetry data for the survey. We actually went back and forth across these lines like 4 times, because we went to do MCS, we came back to do MCS, then we went back and to deploy the OBSs, and then we went back to retrieve the OBSs. And so in each time we did this, we also did multi-channel, swath bathymetry. And so that actually built us a really good set of data for what was going on here. This is the overall seismic section going from the Puysegur Trench up to the Puysegur Ridge and then into the Solander Basin, which we had thought was going to be oceanic, but it wasn't. And then these are blow-ups of the details of what we saw in the seismic reflection data right at the trench here, where this Australia plate is being subducted under the Pacific plate. And then some of the other details of the fault systems that you can see here in the basin. So the overall answer to this problem was that on neither of these lines did we actually see oceanic crustal signature for the velocities in the Solander Basin. We did actually get to an area where it looks like there's a sliver of oceanic crust stuck in here along this fault system. And the overall conclusion from putting all this together is that for a model for the seafloor development here, here's the Puysegur Trench, here's the Solander Basin, here's the Puysegur fault system, and maybe this little sliver right here is actually oceanic crust. And then the rest of this Solander Basin actually is extended continental crust. And then this follows down to the McDougall Ridge and this other seafloor that was formed in the Emerald Basin by spreading between the Australia and Pacific plates back at the time when this was a rift system. But we have to think about, well, so what actually happened? How did we get from, where's the continent ocean boundary right here? And it looks like it follows this line approximately, so that the Solander Basin is not oceanic, it's extended continental. And the series of reconstructions that we have that show this would be more or less this set here. Let's see. I just want to make sure I'm not talking too much. So this is at Sorry. Okay, the first one is 45 million years ago here. 45 million years ago is right when this boundary started, right when the Tasman's basin stopped spreading and we broke a new rift between these two pieces of continental material on the, this is like going to turn into the Pacific Australia plate boundary. And so here's a new rift system here. This is at around 30 million years ago. And we did have seafloor spreading between Australia and Pacific here in this part of the rift. But it turns out that north of that boundary, all of this stuff which was developing in the Solander basin was actually continental extension. So we went from having a long strike ridge system with seafloor spreading to a continental extension system that was not yet forming true ocean crust there. It was still continental. And so if you go then to this 20 million year picture here, what you see is that because of the way the spreading directions changed as the Pacific Australia poles were moving, you ended up with really curved fracture zone systems, and you ended up with this really curved edge to this Solander basin, which is this extended continental crust. So what happened is that all of this Solander basin crust, which was in the middle of the rift initially, ended up getting stranded on the Pacific side. So instead of having like a symmetric rift system where you got equal amounts of continental extension that were then, preserved as a rifted margin sequence as you developed seafloor spreading, all the continental extension parts ended up on one side. And then what was left for Pacific Australia, as it was developing the strike subsystem here, turning into the Alpine fault system, it all ended up on one side. And so the idea here is that probably where subduction started, where subduction first initiated, is that this boundary between the oceanic crust that was formed by Pacific Australia spreading, and then this spreading province that was extended continent, but all ended up on the Australia side of it. So then after that happened, this now pictures like 15 million years, we ended up developing a strike subsystem here that had all of the Solander basin extended crust stranded on the Pacific side. And then a little tiny bit of this blue stuff, which is actually left along the Puysegur Ridge and the Puysegur Trench, is actually a sliver of oceanic crustal material that was preserved. And we know this from the gravity model, and we know that's like a deep, more dense section of crust from everything else that's around. So that was the story, was that we realized actually the stuff we thought was going to be oceanic crust up there wasn't, right? It was extended continent. We would never have been able to figure that out if we hadn't been able to do all that seismic profiling, to look at the seismic velocity structures and understand how much extension had happened and how, what the crustal structure was compared to what you expect it to be for oceanic crust. So let's see. The next thing I wanted to show you actually was something having to do with what's going on right now in terms of figuring out the Macquarie Australia boundary. And that is derived from looking at this paper here, which is from 2020, and they're looking at large earthquake sequences. So these are all really big earthquake sequences. And there was one that was down here in this region in 2004 that happened to it happened almost right at the same time as when the big Indian Ocean earthquake was that caused the tsunami that flooded Thailand and, caused the deaths of all those people. So everyone was focusing on looking at Indonesia and that tsunami in the Indian Ocean, and they didn't actually pay a lot of attention to this big earthquake that happened down by New Zealand. And so this paper came out, Tracking High Frequency Seismic Source Evolution, the 2004 magnitude 8.1 Macquarie event. And so the question is, well, how did we get this earthquake? Was that along the plate boundary between Australia and Pacific, along Macquarie Ridge system, or was it something else? And the proposal was that actually it reactivated fracture zones. So it wasn't actually on the modern boundary. It was like off to the side, in which case it would be part of the diffuse deformation zone between Macquarie and Australia. And so I remember when we were looking at the seismicity to figure out, well, where's the northernmost edge of the Macquarie Plate? Maybe it's up here someplace, you know, it might not go all the way to this margin here, but we still don't know exactly where it is. And so the question is, we don't think it necessarily reactivated fracture zones, but we're not sure because we need more data. We do have one example that some of you may have studied, which is this 2012 magnitude 8.6 earthquake sequence that was in the Indian Ocean. Is this familiar to you guys? It had this amazing set of ruptures. There were like 3 orthogonal faults here that went this way, then that way, then this way, right? And a lot of people thought, well, okay, sure, this must have been reactivating a fracture zone, but actually it turns out it didn't. So for some reason, it broke through this region here, and we know from the gravity modeling, from the magnetic data, this is from EMAG too, but we know from the magnetic data what the trend is of these fracture zones in here, and we know it wasn't actually parallel to the way this ruptured. So this is also a mystery. It looks like this, you know, idea of you being able to reactivate an old fracture zone may be not really true. We think in the case of this magnitude 8.6 earthquake that it broke crust and mantle, but it was in a zone of diffuse deformation in the oceanic plate. It was between India and Australia, right? And so it could be a similar setting to what we have at Macquarie, which might also mean that you can have these big earthquakes in these diffuse deformation zones. There's other ones that were originally assumed to be reactivating fracture zones, but later were turned not to be doing that. And that includes the 1998 Bellini Islands earthquake, which is down in the Antarctica plate, not near a plate boundary, and was also originally thought maybe it was a reactivating a fracture zone, but it turned out to be orthogonal to it, as well as this 2012 one that we mentioned. So the latest thing is that there was an attempt to actually, there is an ongoing study by Hiroya Talkik and colleagues, Caroline Eek and Mike Coffey, Nick Rollins, and I'm part of this group, is they put out ocean bottom seismometers around Macquarie Island. And the idea there is to actually get a better idea of the seismicity right along this part of the plate boundary. And I was talking at lunch to some of you guys about this topic. You can go look at this EOS article. It's really amazing. It's called Deploying a Submarine Seismic Observatory in the Furious 50s, which is a really bad part of the ocean to work in. And they also didn't give the ship the best time slot, like you'd rather go in December or January, not in October. And then also because of the pandemic, I wasn't allowed to go on board because the Australians would only let people from Australia sail, so they wouldn't let anyone else come into Australia. And then to retrieve the seismometers, the ocean bottom seismometers, they retrieved them in 2022 they contracted a New Zealand ship, and then the New Zealanders wouldn't let anybody else go work on the ship, not even the Australians. So the Australians couldn't go get their seismometers back either. But we're looking at that, and they're going to be having some talks about this at the EGU meeting, I think. But the idea is to look at the patterns of seismicity in this region. And my real interest in this, of course, is to see whether we can tell anything about how the Australia plate and the Macquarie plate are separated, and can we see that? So the results are going to be, we'll see the local earthquakes, and so the focal mechanisms will be important for testing Macquarie plate motion. We'll try to see where the northern limit of the diffuse deformation zone is. Once again, look at this issue of, do the fracture zones actually get reactivated? And we also did get abyssal fabric and fault traces, which we can help use for high fidelity plate motion histories, which is almost, that's about, going to be coming up when the work is being done. So we still have a lot more work to do from those 2 cruises. But in the meantime, to get, let's see, how much time do I have? Should I stop? Oh, okay. So I'll finish up by showing you some more things about subduction initiation. So the idea to go back to look at the Puysegur survey and the idea of the subduction initiation was to kind of test these two models for how do you start subduction, right? This is from Cremieri from 2022. And the idea is that you could horizontally force the subduction to start, in which case you need a lot of forces external to be able to get subduction starting. Or it could be vertically forced if you have enough of a density difference to drive it by having dense materials sinking underneath. And as this cycles down into the mantle, then you could get start the subduction. And so the idea for what was going on in the Puysegur area with the Langseth cruise that we did and these results is that we decided that the subduction initiation actually started in this really skinny little part of this plate boundary where the Solander basin crust, which was extended continental crust, was sitting there. And the southeast Tasman basin, which was formed by Australia Pacific spreading, actually was oceanic crust, and so there was a density difference, and that's what started getting it to subside and subduct. And so it wasn't like a big area, but it was just this one area where it had like a crustal density difference enough that it could get the subduction started. And so the next question is, well, okay, so we have these two profiles that we did here for the SISI project, Australia to Pacific on both sides, and we went over the Puysegur Trench. We looked at the tectonics of the upper plate. And then the question is, well, yeah, we know we have subduction up here. Uh-oh, the battery's going low. Okay, well, that's fine. We're almost done. Okay, so the idea here is that we actually have models, and you can look at these for the differences in these three transects going all the way up to the South Island of New Zealand. And so the idea here is that we have some oceanic crustal material, which is probably right here in this area, just take to the west of the Puysegur fault system. Okay, and then we have some basins that developed in the upper plate that we can use the stratigraphy of these to develop, to sort of determine the history of how uplift was happening in this region as subduction initiation was starting. Okay, I think maybe I'll just stop there by suggesting that if you guys are interested in this, there's this whole other paper that Brandon Schuck was first author on where it looks in much more detail at the stratigraphy. It comes also with a master's student, Patel, who did the details of linking the stratigraphy here to a drill hole that was offshore the South Island of New Zealand. So we end up with a really nice history of deformation. And we know when things started from basically how the sediments were deformed and the faults were moving in this whole region south of the South Island of New Zealand. Okay, I think that I should probably end there, but I'd be happy to like show you the video again or answer questions or do whatever you have interest in from this project. Thank you.